Hey guys, today we'll be doing Kosaraju's algorithm. Okay, so first question, what is this algorithm for? We use Kosaraju's algorithm to find the number of strongly connected components in a directed graph. What are strongly connected components? A directed graph is strongly connected if there exists a path between any two of its vertices. Let's see, for example, we have this graph. Okay, so uh, by it has to be directed graph. That is the first requirement. Second requirement is strongly connected components. What is a strongly connected graph? A strongly connected graph is in which there exists a path between any two of its vertices. For example, here from 1 we can go to 2, from 1 we can go to 4, and from 1 we can also move to 3. Let's check it the other way around. From 2 we can go to 1, from 2 we can go to 3, and from 2 we can go to 4. Similarly, from 4 we cannot go anywhere, but from 3 we can go to 4, from 3 we can go to 1, and from 3 we can also go to 2. 4 here is not a part of the connected component. Here 1, 2, 3, this part will be one connected component and this would be a separate connected component, because from 4 we cannot go to 2 or 3 or any other vertex. So this graph in general has two strongly connected components. That would be 1, 2, 3 and 4. Okay, so a strongly connected component is a maximal strongly connected graph. This is a strongly connected graph and this is a strongly connected graph, while these two are different strongly connected components of this complete graph. Now let's look at this example. We can see from 1 we can go to 3 or 4 or 5. From 1 we can go to 2 as well. From 2 we can go to 1, 3, 4, 5. Okay? From 3 we can go to 2, 1 and to 4 and to 5. But from 4 we cannot go to 3 or 1 or 2. So let's just consider this part. This is a separate strongly connected component. This is one component. Then let's consider this. We can go from 4 to 5, but we cannot go from 5 to 4. So these will be two separate strongly connected components. We have three strongly connected components here. Now let's consider this example. In this example, from 1 we could go to 2 and to 3. From 2 we can go to 1, but from 3 we cannot go anywhere. So 1 and 2 form one strongly connected component, while 3 is a separate strongly connected component. This has two strongly connected components. This is an entire single graph. Now, what is the logic behind Kosaraju's algorithm? It uses the fact that the transpose graph has exactly the same strongly connected components as the original graph. Now we need to see what is the transpose of a graph. Now, transpose of a graph is the same graph with just the direction of the edges reversed. For example, we have this graph here, right? If we try to form its strongly connected component, its transpose graph, we place the vertices at the same places and just reverse all of the edges. This would be here and 3 to 1, 3 to 2, 4 to 2 and 4 to 3. If this is G, this will be G transpose. Now, Kosaraju's algorithm uses depth first search. So let's just revise depth first search. Okay, so it is an algorithm which is used to visit every vertex of a graph, or it is used for traversal of a graph. It uses stack for implementation, and it is a recursive algorithm. We have an example here. Let's take this graph. Okay, let's say the starting point of this graph is 1. Okay, so we explore this node, mark it as visited 1. Next, from 1 we can go to 2. We find unvisited vertices and keep on exploring until there are no other options, and then we backtrack one step. From 2 we have 9 as an unvisited vertex, so we'll mark it as visited, put it here. From 9 we can go to 3 or 7. Let's say we go to 3, we mark it as visited. Now from 3 we can go to 4 or 5 or 6. Let's say we go to 4, we mark it as visited. Now from 4 there are no other unvisited vertices, so we come back one step at 3. From 3 we can go to 5 or 6. Let's say we go to 5. Now from 5 we can go to 8. Let's go to 8. 8. From 8 we can go to 7. We take 7. From 7 the only unvisited vertex left is 6. We go to 6 here. Now there are no other unvisited vertices left. So this would be the DFS traversal of this graph. Okay, now let's try DFS traversal for this directed graph. Since it has lots of vertices, I'll be using a stack. It will be easier to maintain a record. Now let's start from H. We put the starting vertex in the stack H. Now we'll mark it as visited. We pop H. We explore its neighbors. From H, where can we go? We can go to A, and this is unvisited. So we'll mark it as visited, put it in the stack. Okay. Now we pop the top element, print it out. Now A, from A we can go to B or D. Let's put it in the stack, B and D. Okay, now we'll mark it as visited and visited. Pop the top element, D. From D, where can we go? From D we can go to F. We mark it as visited and push it in the stack. Now from we pop the top element, F, print it out. Okay, from F, where can we go? There is no other vertex we can go to from F. So we pop the next top element, which is B. Print out B. From B we can go to C. Push C in the stack, mark it as visited. Pop the top element, C. Now from C we can go to E or G. Mark it as visited and put it in the stack. Now from G we pop the top element G. From G we can go nowhere else. All the other vertices are already been visited. There are no unvisited vertex left. So we'll pop out the next element, which is E. E, nothing left. So our stack is also empty. Now this would be the DFS traversal for this directed graph. Now let's move on to Kosaraju's algorithm. I have taken this graph. We need to find the number of strongly connected components in this graph. How will we proceed? We'll do DFS traversal on this graph, and we'll mark the starting and ending time count. Time count is something like, first I went to this vertex, from here I went to this vertex, so I'll put increase the count here. Then I went to this vertex, I'll increase the count here. Like this we record the time count of all the vertices and we use it for DFS traversal and further queries. Now what we'll do, we'll start from this, mark it as 1, we mark it as 1, we start from here, and from 0 this would be visited. Okay, visited. From 0 we can go to 1, let's go to 1, we mark it as 2. From 1 we can go to 2, we mark it as 3. These are the starting counts. When we come back to it, we'll mark its end count. Okay, so next from 2 we go to 3, we mark it as 4. From 3 we cannot go anywhere, so we end it right here. From 3 we can actually go to 0, but it's already been visited, so we won't go there again. We mark it as end. Now we maintain a stack here. What this stack does is, we'll use it for the next step in which we do DFS traversal of the transpose graph. As soon as we end, as soon as we write the end time count of any vertex, we push it inside the stack. Now at 5 we ended our first vertex, we'll push it inside the stack. 3 goes there. Okay, next step, we'll backtrack. Like in DFS, we backtrack when we have no other options. From 2 we can go to 4, it is still unvisited, we'll mark it as 6. These are time counts. Okay, so from 4 we can go to 5, this would be 7. From 5 we can go to 6, this would be 8. From 6 we can go back to 4, but it's already been visited, so we end it right here. As soon as we end it, we'll put it in the stack. Now from 6 we backtrack. Where were we? We were at 5. From 5, is there any other unvisited vertex left? No. So we'll end this as well and push it inside the stack. Now from 4 we backtrack. This was 7, we come to 6. This was 4, vertex number 4. At vertex number 4 there are no more unvisited neighboring vertices left, so we'll end this as well. Now we'll go back to count 3, right? We have to add it in the stack as well. Now from this vertex there is no other unvisited vertex left, we'll end this, push it in the stack. From this we come back to 1, no other unvisited vertices left, we'll mark this as ended also, push it in the stack. Here 0 is also ended, we push it in the stack. Now the point is, there are still 2 unvisited vertices left, so we'll perform DFS on it. We'll mark it as start count 15. From 7 we can go to 8, so we mark it as 16. From 8 there are no other unvisited vertices left, we'll mark it as 17 and push it in the stack. Now from back to 7, right? Back to 7 we can end this, no other unvisited vertices left, we push 7 in the stack. Now we have the stack ready, no other unvisited vertices left, we are done. Now next step is finding the transpose of the graph. Now this is graph G, so its transpose would be something like 0, 3. First we write down all of the vertices as it is. Next step, we reverse all of the edges. We will reverse all the edges. You need to be very careful with this. Now what we'll do is, after reversing all of the edges, we'll pop one element out of the stack and using it as the starting vertex, we'll perform DFS traversal, and this will give us the strongly connected components. Let's do this. We have at the top, we have 7. Let's pop it. We pop 7 here. We'll do DFS on 7 now. So 7 is visited. From 7, is there any other vertex we can go to? No. So we'll end it here. This gives us one strongly connected component. 7 would be one strongly connected component. Okay. Next, we pop 8. 8. It is unvisited. We'll mark it as visited, increasing the time count. Now from here 8, we can only go to 7, but it has already been visited. So we can end this right here. So the second strongly connected component is 8. Okay. Next we'll pop 0 from the stack. 0. Let's put the count here. 5. From 0 we can go to 3. And from 3 we can go to 2. From 2 we can go to 1. And from 1 there are no other unvisited vertices left. So we'll end it here and go back. No other unvisited vertices left. We'll end it, 10. We'll end it here. In the next connected component, we'll keep adding it here. 1, 2, 3. No other unvisited vertices left to visit, so we'll mark it as ending and add it here. Now back to 0. 0. No other ways to go, so we'll end this as well. 0. We get our third strongly connected component. Right? Next up is 1, but 1 has already been visited, so we forget it. Next 2, we pop 2 out, but it's already been visited. Next up is 4. 4 not been visited, so we'll mark it 13. Right? From 4 we can go to 6, we'll mark it as 14. From 6 we can go to 5, this would be 15. From 5 there is no other vertex which has been not visited yet. So we'll end it, and the fourth strongly connected component, it would include 5, then back to 6 and back to 4. We get another strongly connected component. 4 does not have any other unvisited vertices left to be visited. So this graph here, this was the original graph, this was the transpose graph. Don't you get confused. Okay, so the original graph has 4 strongly connected components: 7, 8, 4, 5, 6 and 0, 1, 2, 3. This was Kosaraju's algorithm. Now stating the algorithm in, I've written it down. You can pause the video, take a look at it. We created an empty stack S. So we created an empty stack S first. We did DFS traversal of the original graph. During the DFS traversal, we note down the start and end count. Then we write the end count of a vertex and push it in the stack. Take the transpose of the graph now, pop an element from stack S, and using it as the starting point, perform DFS traversal. Next, this DFS traversal will give us one strongly connected component, and we'll repeat this until stack S is empty. Now, looking at the time complexity, DFS traversal of a graph, we visit all of the vertices and we visited almost all of the edges. So the maximum possible time complexity would be the maximum of the two. So we write it as order of V plus E, big O of V plus E. V is the number of vertices, E is the number of edges. Thus overall complexity, since we are performing DFS traversal twice, on the original graph and on the transpose graph, there are no other operations that we're performing. So we did DFS twice, the overall complexity would be big O of V plus E. Now, what are the applications of Kosaraju's algorithm? This may sound a little weird, but it has been asked in the examinations many number of times. So, what are the applications? Kosaraju's algorithm can be used as a first step for graph algorithms which only work on strongly connected graphs. So there are some algorithms which only work on strongly connected graphs. So we need to find what are the strongly connected components in the original graph and then work on it. So we use Kosaraju's algorithm as step 1 in those algorithms. Next is social networking sites and apps use it. So for example, there are a group of students of a class. We consider them as strongly connected. They have similar interests, almost, in considering academics only, if we see, and they are of the same age group. So we can use Kosaraju's algorithm to find these strongly connected components and suggest them commonly liked pages. So this was the applications. The pseudo code I'll be giving in the description, and if you have any doubts, comment it below. Thank you very much for watching.